Okay, it's a 2013 question 9 exam, an unknown organic compound with a molecular formula. So you don't need the mass spec information to work out what it is. You do need to know there's multiple isomers of this, and they've given you some different spectra, and they've said what they think it is. So you don't actually have to work it out what the molecule is going to be. You just need to show a link between the molecule and the spectra. So they've shown you here how they want the question answered. So there are four signals on the carbon NMR, which indicate four different carbon 13 environments, chemical environments. And then so that's from the spectra, and then it's showing you on the molecule. This particular molecule has four different carbon environments, different atoms bonded to it, different elements, and then the neighbors are also different. So that's what they want you to do, to look at the spectra and then to link it to the molecule. I was looking at this question to see if it would be possible to answer this question, even if you didn't know what ethyl ethanoate was, and it kind of is. The mass spectrum, the first would become positively charged, and it would move through the mass spectrometer and because of an electric field, and then it will bend in the magnetic field. Depending on the size, you need a higher and higher magnetic field, which indicates a larger and larger mass. So the largest peak that you get is the whole molecule, and we call that the parent peak. So date, what are you getting from the spectra? So the parent peak is what I'm looking at, and that parent peak you need to quote so that we can identify which peak you're looking at. So quote the x-axis and use the units. So just in this case, you can say the MZ value at 88, the peak at 88, is, now link that to the molecule, is consistent with the molecular mass of the actual molecule. And this is the ion. So whenever you see mass spec, try and remember that the molecules or the fragment that you're talking about is a positive ion, so that they'll be looking for that. So that's the whole molecule. It's the same as that, the same size. So if you added it all up, how big it is, you find it's the same size. They also accepted if you looked at some of the fragments. So this is the biggest one, the base peak, and it is at a size of 43, relative molecular mass of 43, and so half the molecule here. So if you were quoting a fragment, you'd have to say this particular fragment has a mass of 43. So you get one mark for your linking the spectra correctly to the ion. The infrared, so we've got our peak here, our peak around 1700. So you've got a strong peak. You need to label that it's this strong peak. And it is consistent with the CO, the carbonyl peak, in the ethyl ethanoate, which would be present for an ester. So for an ester, because there's a whole lot of these with different, let me show you the thing, different carbonyls depending on the situation. So when you're looking at the one for the ester, then talk about the, interesting, I've copied that off the exam answers. Okay. So it should have been 720 to 1840 here. So the 2013 exam answers are wrong. All right. So they also accepted, so anytime you see two oxygens, you'd be tempted to think that it was a carboxylic acid as well. The OH group, hydroxyl group here, and that together. So they also accepted that it can't have been a carboxylic acid because of the absence of the OH bond that you would find in a carboxylic acid. So you'd need to look at the data for the here that you're missing and quote this 2,500 to 3,500 and use your units whenever you're quoting these numbers. There's on the hydrogen NMR, so there's a whole lot of things that you could have said about this and you didn't need to say all of them. So if you'd said this one correctly, so there are 3 peaks. The first thing that you look at, you've got 3 peak areas, which means that there are 3 hydrogen chemical environments. So there are 3 peaks on the spectrum, which is consistent with 3 hydrogen chemical environments in the molecule. So link the spectrum to the molecule. There's also a triplet here. So this molecule, these 2 are the neighbours, so 2 plus 1. This peak, for the 3 hydrogens here, would be split into this triplet, these 3, because of the 2 neighbours, 2 plus 1. And these have got 3 neighbours, so 3 plus 1. These, the peak that's due to the 2 hydrogens, will be split into 4, into a quartet, because of the 3 hydrogen neighbours. Okay, split into a quartet. Or if you can see that it's a quartet, it's been split into that because there are 3 neighbours, hydrogen neighbours. So if you talked about that, if you're talking about the triplet, they want to know that you know what a triplet is. So if you link that to the x-axis, so using your units, so it's at the triplet at 1.23, so they know that you know that that's a triplet. And the quartet here are consistent with the splitting pattern caused by this in the ethyl ethanoate, so you've linked it to the molecule. Or you could use the chemical shift information, and I haven't written down that. Okay, so next one. Another compound has the same molecular formula as ethyl ethanoate, so it's an isomer. However, the carbon NMR for this shows only 3 peaks rather than 4. So whenever you see something, if you've got 4 carbons but only 3 peaks, it means that there are 2 carbons in the same environment. There's 2 ways really that you can get that. If you have a symmetrical molecule, so the carbons CH3s on either end have exactly the same things that they're next to, like a propane, then they would be in the same environment. So symmetrical molecules, or if you have branching. So it's difficult to get a symmetrical molecule when you've only got 4 carbons and one of the carbons is with a carbonyl group. So the other way of doing it is if you have branching. So it didn't say if this other compound is an ester or a carboxylic acid molecule. So these are 2 that would have 3 signals. So you've got 1, 2, 3 carbon environments, 1, 2, 3 carbon. Okay, I just want you to get used to thinking when you're given a molecule that's got a certain number of carbons, hydrogens and oxygens, that you can make lots of different isomers. So if you're trying to work between them, do it consistently. So anytime you've got 2 oxygens, it kind of lends itself to an ester or a carboxylic acid. That's what we're tending towards. But you can put the oxygens in other places. You could make an aldehyde with an hydroxyl group on it, or ketone with a hydroxyl group on it, or because it's C4H8, 4,8, it's double the amount of hydrogens, so there has to be a double bond somewhere. The double bond doesn't necessarily have to be between the carbon and the oxygen. It could be between carbons and carbons. I needed to throw in an extra oxygen here, so you could put an OH on here and you could put another OH on here. So I'm not going to do this again. This will do. So just get used to thinking outside the box, because they have done things where you've had a double bond between carbons with hydroxyl groups for the oxygen rather than like this. If you're trying to work between esters, do it systematically. We've got 4 carbons to play around with. So this would be your alcohol joined to the carboxylic acid. So just put 3 maybe on your alcohol and 1 on your carboxylic acid, and then take one off and put it over here. So you've got 2 and 2, which is what our molecule was, and then take another one off and put it over here. So you're systematically working out the combinations. And then once you've got 3 in a row, you could take one off and put it over here. Or take one off and put it over here. 1, 2, 3, 4, 5. Okay, I've done the classic mistake here, which is probably good to talk about. Students, and I did apparently, this carbon here tends to become invisible. So you don't count it when you're counting carbons. So what I've done here is gone 3, 4 and not counted that one. So when you take it off here and put it over there, you're just adding 1 more. There shouldn't be 3 here. Okay, so you see this sometimes where you ask somebody to draw a molecule that's got 4 carbons, and now they will draw you one that's got 5. So this should have had 2 here. Sometimes it doesn't hurt to make mistakes, and then you can see. So always start with your straight chain first. So you've got 4 carbons in a row to make a carboxylic acid. Carboxylic acid is always on the end, so the only other thing you can do is take one off here and put it on the middle. You obviously can't take one off and put it on here because this has already got 4 bonds. Okay,